And the camera, oh, why?
You're early, right? Sorry? You're early. You're starting at 6.
I think you was looking at, maybe you started about 9.
Whenever you want to start.
You got some light changing the place?
No, it was just the first administrative, like the car just went by, like the track, that wait for the next one. But yeah. I was planning to connect to my computer, but then he said that he wants to use his because but if it costs, it was like 650 megabytes. It's gigantic. It's okay. No, I think it's I think it's fine. I think I'm just hoping that the videos because the problem is that it's the Mac it was made on Mac, so sometimes it's on PowerPoint, but it goes on Mac. Some of the videos don't run. But we'll see. Some of the fonts get lost. It's okay, no worry. We'll figure it out. That's fine. More worried about you now.
We try to make it working.
So I don't think we need to push the other so I won't forget it. Okay. It's okay.
Yes, microphone. I will fix it if you wish next to you, but no, we don't have the remote, but it's very powerful. When I did my test yesterday, it was very warm. Yes, and you walk here, I place another one here. So even if you are here, people will control the microphone. For the speakers,
Tu sais que c'est un excellent sujet. Non, c'est bon, c'est le seul que j'ai délégué. Je répète.
If you need just 5 minutes, then we'll start.
Same sponsors and so on. If you wish, we can stream the presentation of the open speech. Do you want to speak?
Let's say Nicolas, you can start the streaming whenever you want. Commence quand tu veux. Nous, on va commencer parce qu'il ne faut pas qu'on prenne de retard. Si t'as que la moitié, c'est pas grave parce que c'est pas long. Ok, ça marche. Bon, bah. C'est bon?
Ah oui, partage la gauche. Ouais. Il faut projeter sur ce slide. Moi, je
On aurait Rémi parce que c'est Rémi qui se fait ça d'habitude. Celui-là, il marque. This one works.
Okay, good morning, dear colleagues, dear attendees, good morning everybody. I'm Alex Rodarax, General Co-Chair of Wireless Power Week. On behalf of the organizing committee, I would like first to thank all the attendees and also our platform sponsors, Electronic, Electricity, Energos, Airfuel Alliance, GAM System, Vivo. I would like to thank Bordeauxville and our mother society, IEEE MPT and IEEE PENS. And
microphone is not working.
Sorry?
Microphone is not working.
Yes, I think. Okay, everybody hear me? I need to speak.
It will be possible, but without this noise from outside.
Okay. If not, I will try to speak as strong as I can.
I think tu gardes ton masque. Ok. Tu gardes le masque et tu touches. Si tu touches, ça marchera. Il faut que ton micro il touche ton masque.
Okay, it's okay now?
Yes.
Okay. I'd like to thank our mother society, MPT and BELS, and also our local sponsor, Bordeaux IND, also ILS, Amcar Engineering, Albacross, and also Bordeaux Tourism and Congress. And I would like to introduce now our co-TPC chair, Professor Luca Rosselli. Luca, it's your side.
Thank you, Alex. Good morning, ladies and gentlemen. Usually, when someone is committed to introduce the conference, says something that is similar to, okay, I'm honored to be here, I'm very pleased to be here, blah, blah, blah. So please guess what I'm going to say now to you. Yes. I'm going to say I'm very glad and proud to be here to introduce this conference. But I would like to spend a couple of words to explain why this is not just a formality, but it's a real thing. I I had the pleasure, really, in 2013, after a couple of workshops organized by Professor Naoki Shinohara in Kyoto about wireless power transfer, the IEEE workshops on wireless power transfer in 2011 and 2012, I had the pleasure to be appointed, and my university, my institution was appointed by IEEE to organize the first wireless power transfer conference. Of course, it was, let's say, in a period where wireless power transfer was considered an emerging technology. I remember that in that period, I'm not sure about the precise year, it could be 2012, 2013, I don't remember exactly. The IEEE set up the technical committee of wireless power transfer, along with another couple of committees, RFID and RF nanotechnologies, and they were considered emerging technologies. So wireless power transfer at that time was considered by NTT Society as an emerging technology. And I remember the first conference, it was of course the first one. The dimension was a little bit small, let's say, because eventually we got about 100 of attendees from everywhere. It was very nice, but still, it was a fairly small conference in a small city. Perugia is still 250,000 citizens. And there were a lot of worries about the evolution of this conference. And so, but it was really, really exciting, even though it was a bit thrilling for us to organize this event. After that, there were many follows-up of this event. It was the conference continued to grow and to be held in different places with the rotation of 3 continents, 3 regions, US, America, Asia Pacific, and Europe. And it kept on growing gradually, but not slowly. This happened, and I experienced this growth till 2019, when the conference, the event, joined the, let's say, was joined to the workshop on wireless power, the flagship conference on the same topic of PEL Society, Power Electronic Society. And since that time, the event became Wireless Power Week. And of course, the growth continued. Unfortunately, we experienced there is no need to underline these last 2 years. And I see today that we are still together here to contribute to the success of this event. I know roughly the numbers, and I can confirm that these numbers, the attendance, the quality of papers is still growing. This is really exciting for me. That's the reason why I'm really proud to be here to introduce this conference today. And at the end of my introduction, I want to say to you, to this wonderful community, to the ladies, the gentlemen present here in this room, enjoy the Wireless Power Week. Now I let the podium to Simon, that is our general chair.
Thank you, Luca. So while John is bringing on the numbers of the conference, I'm very glad to be able to welcome you once more to Bordeaux and to the Wireless Power Week 2022. I will go with you through the main highlights of the week. This is the first time that we are holding the conference at this scale, because we are going to have two important evenings. The first evening that we are going to have today is devoted to industry as well as connection. So we will move from the campus of Bordeaux at probably something like 6 p.m. and we'll take the tram to go to the north side of Bordeaux, where you will have, I believe, a very interesting experience on a very interesting building. So today we are going to do some networking, and we are going to have great industry keynote on the evening. Today is also important because we are having the first design competition. This is a student design competition, something that is led by the IEEE Wireless Lower Transfer Initiative. And I welcome you, I invite you to enjoy all of the great demonstrations that we are going to see on site of the conference, on the exhibition board. This is also very great that we have the exhibition and we have many sponsors for the conference. This is a growing number and this is very important for the community. This is probably everything for now. I will hand over the microphone to John Paul from the University of Singapore. And thanks again.
All right, thank you so much, Simon, for planning this incredible conference at this beautiful location. My job here for the next few minutes is to regale you with some statistics about this conference. So overall, we've received 225 submissions to this conference. It's of course lower than the previous year because that was entirely online. So given that this conference was specified to be in person from the very beginning, we're pleased with that number of submissions. The total acceptance rate has been about 80%. Of that 80%, taking the overall percentage, 36% of the papers were selected for oral presentations and 44% for poster presentations. Even though a lot of countries have not opened up for travel yet, overall about 80% of those oral presentations will actually take place on site here during this conference. It's interesting to see the breakdown of papers over the different countries. Interestingly, the top number of submissions was from Japan. So if you're from Japan, I guess a round of applause to you. Thank you for submission. Our second most was actually France, which is not surprising given where we are. Actually, United States is a bit low. This is an older slide before we counted the latest submissions. United States should be actually, I think they've overtaken the French since the late 80s. We've got also submissions from all around the world, and you can see the majority is from Europe, Europeans and Africa songs, and the about equal around the Asia and Oceania. Finally, it's interesting to see when the submissions happened. Unsurprisingly, the majority happened right the day before the deadline. For those who submitted early, thank you very much. So that's the overall statistics for today. Simon, I guess over back to you.
Yeah, thank you very much. Okay, thanks a lot, John. So today is going to be probably the longest day of the conference. So I'm going to ask the chair to be very careful about the timing of every session. Time is written in your printed booklet, so we will need to keep the time because we have a very long and very full of session day. So I would remind you that unfortunately we are in some new spread of the virus. So our recommendation is that if you are sitting and there is some space around you, this is probably okay to remove the mask. But if you are in close contact with someone during the cocktail or in discussion, this is probably a good thing not to leave your mask away for too long time. The place where we are going to meet this evening is a place that is rather confined. So I will also ask you to bring your mask this evening with you. If you feel that there are too many people in the transportation, this is also something that would be important for you. As you know, there are many conferences that are being held on this side, and most of those conferences are just sending an email at the end of the conference saying, sorry, but this was probably a super spreader event that you went through with us. So I would prefer not to have to send such kind of email. So I hope that everyone will be safe during the week and returning home. Thanks again for your attention. And now, John, I will ask John and Ali to come on stage, and John will be introducing the opening keynote of the conference. Thank you very much.
It's my pleasure to introduce Professor Ali Hajimiri from the California Institute of Technology. He is the Bren Professor of Electrical Engineering and Medical Engineering. Prior to taking on a faculty position at Caltech, he was working in industry under Philips, I believe. So we're really excited to have him here today to speak about radiative power transfer in all forms, all the way from sort of the room scale, like us here in the room today, to space. Over to you, Professor Hajimiri.
Thank you, John. Thank you, everyone. Good morning, and hope you're enjoying the beautiful video. So, I am. Can everyone hear me?
Yeah.
Tell me if you can. Anyway. Okay. So we are going to talk about. I'm going to give you a little bit of an overview about wireless power transfer at the distance and our progress on that. Give you a little bit of an overview. Obviously, this is something that's important to everyone, from your living room, as John mentioned, to even extending it to outer space and transferring energy from space to Earth. And I'll give you a little bit of a snapshot of each one of them. One of my pet peeves about plenary talks is that when you listen to some of them, they have a lot of vision and very little content. So I'll try to not to do that. I'll try to give you a lot of content. So there will be equations there. So this is a good time to leave if we do a lot of equations. Okay, so let's get started. What do we mean by true wireless power transfer? We mean intelligent power transfer that can go, that will be available at the time you want, the amount you want, and where you want. So basically where you want, when you want, and as much as you want. Now, this kind of power transfer, of course, presents many, many opportunities. There are basically endless opportunities in many different sectors. I don't need to preach to the choir in this conference. A lot of other places I have to tell them about the possibilities, what you can do, but there is no limit to what you can do. And these are some examples of the things that you can do from various segments of the industry, anything from your mobile devices to various kinds of systems. All right. So let's kind of talk a little bit more about some of these examples and how we go about doing that. Okay, let me try a different way. Right. So while we're working to figure this out, basically it's important for us to know that there are many things that we can do with power. Obviously, again, most people here know about that. But Essentially anything with a battery, or a power cable, or even without, can benefit from energy transfer wirelessly, and that's what really matters in our system. So now, let me just try one more time. Yes, here we go. So what is our vision? I'm going to present you some of the visions that we've had at Caltech and Google's and Caltech spin-off. By the way, full disclosure, I am co-founder of Google Wireless. So now, what we call for the terrestrial applications, we are thinking about things where you can transfer multiple watts to multiple devices at multiple meters with real-time tracking. So this is the kind of system that our vision promotes and we'd like to see. So there are different applications, very different power levels. Some applications require microwatts, and that's a very different kind of application. The kind of applications we are focused on really fall in this category. Multiple watts, multiple meters, multiple devices, and real-time tracking. So for terrestrial applications. And then when we get to space power transfer, then we'll talk about gigawatts and things like that. Megawatts and gigawatts. Things we'll get there in a few minutes. Okay, so a little bit of a background about our technology development, and it's interesting, this came out of some of the technology development that we did at Caltech before, which was the millimeter wave systems. Now they've become commonplace. We started this millimeter CMOS power transfer, and I made a statement 20 years ago, which I will make about wireless power transfer. We were doing millimeter wave phased arrays back then for mostly for communications. And then this technology also that we saw the potential of using integrated circuits, high-frequency integrated circuits, to make a cost-effective solution for wireless power transfer at shorter ranges. Now, the basic concept, let's go overview it here, it really goes back to this concept of interference, which is a very well-known physics concept in physics. I'm sure everyone knows here about it. When I try to tell people who don't know less about it, I use an example. Let's try this as a fun example. So I want everyone to think about your favorite one-digit number. Think about it. Your favorite one-digit number. And on the count of 3, I want you to say that number out loud. 1, 2, 3. All right. Now I want everyone to say my favorite one-digit number on the count of 3, which is 5. Okay? So again, 1, 2, 3. Okay. So that's the difference between coherence and incoherence. Right? Kind of, but close enough. Now, so you see when you have coherence, you have constructive addition, and that's basically the way you get constructive addition, which is basically what you see in this video, what you used to see in this video. Yeah? I assume that you're the same. Anyway, so now, if you have more than one source, you can obviously control the behavior of the system by having all of them in phase. So in this example, you have 10 sources going in parallel at the same time. And what you see is that you can see more and more of the energy being transferred in one direction. In the case of interference, you saw that there were regions where you had more energy and less energy. And then there's basically the concept of the ability to make a phased array. Now, the next benefit of a phased array is that if you control the relative timing of these sources, then you can basically control where the energy goes. So this is the classical beamforming, right? Beamforming is a far-field concept. It has been around for almost 100 years in various shapes and forms, and this is basically the electronic circuitry, advancement of electronic circuitry has allowed it to happen. So by controlling the relative timing of these things, you can make them go fast to different directions and control it. Now, the next level, which is actually what we call a near-field radiating concept, and we'll talk about this a little more, is focusing. Focusing is not a radiative far field. It's basically a Fresnel concept, not a Fraunhofer concept in that sense. So this is basically what you see. You can control the timing so that actually you can create the effect of a lens, an RF lens. But with the difference is you can actually control where the energy goes. And you can control the focal point of that lens. For some reason my videos are not doing it full loop. But anyway, you saw it once. So basically, by controlling the relative timing, you can actually send it to the desired location. Now, at far field, this will be all spread across a larger field. It's not the narrowest thing you can make. But at that specific distance, you can create the largest focal point. And that's the concept of RF lensing that we'll be using in many of these things. Now, to understand that, okay. All right. So this is a kind of picture that you can think about. You can think about an array on the transmitter, on the generation side, which we call GUs, the generation units, and then there are the recovery units, or receiving units, that we call RUs. The GUs basically are an array of elements that get transmitted, and by controlling the relative timing of that create a focal point at the location of the audio unit, where the recovery happens and receiving happens. So this example of RF lensing allows you to basically use this near field radiative concept to transmit energy. Now, when we say near field radiative, what do we mean by that? And how near is near? Because when you talk about near field, people think, oh, this is proximity, near field. And I'm going to give you two examples, two numerical examples, for you to see what that means, and we'll see the implications of that. Now, one example is based on, so what we mean is that to generalize it to two apertures. The idea is that can you maintain an accurate phase variation across the surface? And then if you can use that, the question is that how accurate you can control that. So this is an expression you get, for example, if you want to maintain a certain level of phase. And now this is an important point. So these two examples are not chosen arbitrarily. So one example is an important one. Imagine that you have a generator unit that's about 30 centimeters across and a recovery unit that's 10 centimeters in size, and they're about 4 or 5 meters apart. Now, that's the limit of basically how far they would need to be for you to be radiated far. So anything narrower than that would be radiated near. Now, the second example is also important when we talk about later, when we talk about space transport. This is an array that's 1 kilometer across in generation and 1 kilometer across in the receiving. And the question is that how far do they need to be for it to be radiated far field? At 10 gigahertz. These are two specific frequencies that we're choosing, because that's what the frequencies of operation of those things are. And you can see 66,000 kilometers. Close to twice as far as the geosynchronous orbit, which is 36,000 kilometers. Just keep that number in mind, that an array a kilometer across in space, and a kilometer across in Earth, and 36,000 kilometers geosync is still not radiated far. Okay, now we can calculate the efficiency, and I promised you I show equations, so I show equations. But anyway, the bottom line is that you can actually calculate this accurately, and if you're interested, you can go check out those papers and all those things and find it. But now, there's a way to approximate this, and it really goes back to the following. One way to think about radiated far field is that you can think about the size of the spot you're forming at the focal point. If the size of the spot is smaller or comparable to the size of your recovery unit, then you are in radiated near field, and you can recover the vast majority of the power. Now, this is the first order calculation, like I mentioned to you earlier, there's a more accurate calculation, and this is basically this region of the plot of transfer efficiency. And then, of course, when you drop off, you go into a range where basically you have this radiated field. Now, why is this important? Why is this background important? Because it tells you what happens to frequency. What's the impact of frequency? Why do you want to operate at higher frequencies if you could? Now, you can see that these are 4 plots, at 5 plots really, at 5 different frequencies, 5 different wavelengths. And you can see that that expression that I showed you earlier, it's better and better as you go to higher frequencies. So at lower frequencies, what you can see is that your maximum theoretical transfer efficiency, so this is the maximum you can get theoretically. You can't exceed this number. Drops very rapidly at short distances. But as you go to higher frequencies, what happens is that now you can get farther and farther and losing less and less. So this is an important part because it comes from this lambda at the bottom. So now, through this last 10, 12 years, we've actually made 4 generations of our systems. We call them F1, F2, F3, F4. And what you see is the pictures of that. So it's a similar size system. So what you see at the bottom is a 2.4 gigahertz system with a 2.4 elements. And then you can go to a 5 gigahertz system. You can see the 10 gigahertz system and the 24 gigahertz system. All of them are 2x4 element equivalent. And you can see the relative sizes of these things. And as you can imagine, as you can see, obviously there's a progression and improvement on the size because of that. Now, of course, that assumes that the active components can actually support something like this. All right, so, and then again, what you can see is that you can produce, using high frequency, you can make very, very small recovery units that can actually recover the energy of power the way you would like. So, how does the system work? Now, there are different ways of achieving this, the retroreflective systems and all those things. This approach is different. the way we are doing it right now is that we have a GU and a RU that communicate with each other. And what you do, you can the GU transmits, and you control, by controlling the relative phase and amplitude of the elements of the GU, you can control and the focusing and affect the focusing. Now, this communication channel allows you to do this without having any reflective system, and you can directly communicate and set and focus the system. Now, the challenge here is that if you try to do it in a brute force fashion, even if you think about a very small array of 100 elements, if you have 100 elements on the GU, you are looking and if each one of them can take 256 different phase configurations, forget about the amplitude, it takes a significant time to try all the combinations. So for example, if you go 1 billion combinations per second, that will only take about 3 times 10 to the 213 times the life of the universe to go through all these combinations. And that's only for an array of 100 elements. Beyond astronomical. So, how do we deal with this? Well, the solution is that if you think about this problem, this is a cycloconvex problem, meaning that if you have the right way of approaching it, you can actually climb and have some sort of a climb to get to that optimal point of the phase variations. Now, in theory, this is fine. So you can basically find it. What it means is that you can actually control the phase of each one of them, tune the phase on each one, and get to the maximum phase, maximum power, and then go to the next one, and the next one, and the next one, and continue doing that. And you will do it very rapidly, just basically make it linear time, and then you make that happen. The problem is that when you have a large array, you're trying to detect a small variation in a huge body of power. So for example, imagine all those blue elements are transmitting power, and they are linear focused, and you're trying to see the variations induced by small variations in the phase of that one red element. And the more elements you have, the smaller that variation becomes. So that curve looks flatter and flatter. So it's hard to detect that peak, especially if you have noise, which you always do. If there's noise, then you basically will not see it. So there are different ways to go about this. And one of the methods to deal with that is that you have to create a larger dynamic. The problem is the dynamic. So how do you deal with the dynamic? Now, here's the thing. You can actually don't have to change one element at a time. You can change multiple elements at a time. And you can phase change it. And then, for example, this is a very kind of simple example. Imagine that you take half of the element and move them in one direction of phase, and move the other ones the opposite, or keep them constant and move only one half. Right? This produces a significantly large variations in the power of the receiver. However, the challenge is that if you just do this, you can't hit the optimal for the whole array. You will only hit the optimal for the left versus right. So the question is that can you come up with a method that allows you to not leave these huge blind spots? Because if you just do this, then there are a lot of, you will not arrive at the global optimum. How can you make sure that you span that whole space? And one of the solutions is based on trying to come up with all different variants. So this is another variant. So for example, you can do upper left versus and lower right, combined with the lower left and upper right? And then if you do that, then you have another part of the space, still not spanning the whole space. So what you need really is to create, from a mathematical perspective, an orthogonal basis for these things. So you need to create a different basis for these functions that allows you to span the space completely. And if this basis has enough elements in it that can span this whole n-dimensional space, vector space, then you can arrive at the right place with using very large systems, very large dynamics. Now, on top of that, if you actually make the spaces orthogonal, what it allows you to do is to kind of process these things in batches, meaning that you don't need to do it one at a time and look at the result. You can go through all of them and then look at the results sent back to you from the power receiver. You don't need to do that one at a time. Okay, I changed this, how much did it change? Change this, how much did it change? You can go through the whole batch and process it post. And that's the strength of this thing if you make them orthogonal. So we developed this orthogonal basis, for example. By the way, the content of this presentation, most of it is like published stuff that I'm putting in the references, so feel free to check them out. But you can make these orthogonal bases. This is an example for a 4x8 array. So these sets that are generated from mathematical Hadamard matrices, or a variant on that. So this is not the Hadamard matrices itself, but it's generated off of the Hadamard matrices. You can create these bases and allow it to span the space completely and orthogonally. All of these bases are actually orthogonal to each other, meaning that if you multiply them point by point and add the sum is 0. And that allows you to process them all in batches. So you use these bases, we use these bases, for example, to find this optimal solution. So that's one part of this, the algorithm. The other part is the hardware. I mentioned earlier the promise of using an integrated system, silicon CMOS integrated systems, to integrate all of the functions necessary in an array. An array like this requires a lot of components, and you want to make it in a modular fashion where every chip basically has all the functionalities so it becomes cost effective. Now, that's basically where a lot of these things come in. So for example, this chip on the right-hand side is a chip that we developed in silicon CMOS that has it can drive 16 different power amplifiers. It has 16 different power amplifiers that drive 16 different antennas, radiators. So 16 elements of the array would be addressed by that. And these 16 elements, so this is the block diagram, the top level block diagram of this chip. So there are 4 quadrants on 4 corners, each one driving the 4 different drivers, and then as you go, it has a lot of different functions integrated into it. So if you look at each one of these power quadrants, they're pretty complex. So the level of sophistication actually is pretty high in something like this. Each one of them has multiple levels of power generation. You have a lower frequency 2.5 gigahertz system coming in, 2.5 gigahertz reference clock coming in. You have the phase control, you have the power cores, and you have all of these functions integrated into each one of those power cores. And then if you go farther deeper into this one, each one of these power amplifiers has sophistications and all those things. Again, I'm not going to bore you with the details of this thing. You can check out the papers. But the bottom line is that there's a fair amount of detail. And there are 17 TLLs, for example, on this chip. There are multiple power amplifiers. There's a fair level of sophistication which is important to have to make sure that the solution becomes realistic and cost-effective. So again, there are more and more of the details shown here, like give you a sense of that level of complexity that's involved. So, but for example, these are the CMUs that produce the phase shifts and the clock multiplier units that are digitally programmable and vary in different aspects of the system. So this is a picture of that chip. This is a picture of a board made with that chip. So this is basically the building block. This is the, for those of you who like Legos, this is your 2x4 Lego block. The classic Lego block that you can use to make as many of these things as large an array as you want. And we designed it in such a way that's completely scalable. So you can use it as a standalone 2x4, or you can make arrays with thousands of elements. And I will show you examples of those two in a few minutes. So this is for example a 400 element version of an array that's built here, made out of these unit building blocks. And what this does, it allows you to scale it up. So that scaling is a very important part of this equation. And then these are some examples of measurements to give you a sense. So this is basically shows the focusing. But you can see the focusing profile. This is actually the energy profile in different cross sections in front of the array. So this is basically happening this is at 30 centimeters, this is at 60 centimeters, this is like at different places. You can see the energy is focused and then it's divergent. So there's a focusing and divergent. And then the other interesting thing is that when you actually put a recovery unit, an RU in there, what it does is that you can see that the energy profile remains the same before you hit the RU, but behind it is very small, which is important because it means that most of the energy is absorbed by your receiver, not by the person holding the receiver. So that's an important distinction to make sure that we have this. Now, if you look at these things, so these are some of the measurements for this is for the 10 gigahertz system. The 24 gigahertz is even better. So basically, you can see that you get a couple of watts at distances, at a couple of meters with this system, and then you can see the variation with the angles, and we did tilt angles, and there's a whole bunch of different measurements. Again, I'm just showing you representatives of these measurements to give you a sense of what can be achieved. And this shows you how quickly you can reach the optimum with this system. Again, with the 24 gigahertz system, it's even faster. It's an order of magnitude faster, the time it takes to get to that optimal position. So now I promised to show you a complex. So that was a 10 gigahertz system, and this is an example of 24 gigahertz system. The 24 gigahertz, this example here, this has 4,000 elements. 496 to be exact, to the power of 12. And it's made out of these building blocks, which is like now a 24 gigahertz system, a millimeter wave system. And then you can actually get it integrated into various. And this is basically an example of what you get on the RU, on the recovery unit. It can be very small, very effective, and it can recover a fair amount of power. So, in short, about this part of it, the difference that this makes is really being able to use the millimeter wave with this algorithm and having the state-of-the-art architecture and the single CMOS that allows you to make a longer rate, shorter, longer rate, higher power, more efficient, and smaller size system. Now, I'm going to give you a few examples of these things. So there are some videos of these things to see them in action. Let's see if I can actually play them for you here. This one basically shows you a couple of videos. Here, this video shows you how this system, so there's a little bit of a cartoon in the beginning to show the concept. This part doesn't matter, you conceptual notion. So that's really good. Now, that shows you that this is programmed and how relative this is. So that's a system, for example, of sitting on speed. And to give you an example of this thing, you can see this light bulb, for example, the big power. And once we move it, you can see how narrow the full is, but the system tracks it. How the delay added. So let me show you another example. So this is basically a propeller being powered at a large distance, more than 10 meters. So this one, as you can see, the system sitting in the back and sending wireless power to the propeller that's being fixed here, and the power energy is being transferred there. So now, to give you a sense of the real-time tracking ability and how fast it can happen, this one shows you a car that actually the beam is tracking, the new battery is in real-time tracking. So you can have two to go around and see it. Now, let me show you another example of that. This one gives you a sense of how small your receiver units can be. So this is an example of how small they are compared to a phone that's US quarter, the size of like a little larger for about the same thing as your phone. Now, so this is selecting send it to that small device, this small device. This can get embedded into your devices. For example, this is an earbud that is being charged by this. You can see it. There we go. All right, and there are more examples of that. I mean, like a cell phone being powered, things of that sort. So that's not a problem, but fine. So now let's take it a little bit further. Let's say, okay, what is next? What's the long run? Now, this concept of transferring energy from space to Earth. This concept is not new. It has been around. The earliest version of that came from Asimov, Isaac Asimov, like many other concepts. From 1941, there's a short story that you should read, and it's very interesting because, especially in this day and age, it's interesting to read that story, not because of the wireless power cord, because it's actually a robot that is built and assembled on a space station whose function is to do wireless power transfer, but then it has an existential crisis. It's asking the questions like, what am I doing? Who am I? Why am I here? You know, what am I doing? And then somebody explains and say, okay, all those little dots that you see, that bright dot is a source of energy. You take the energy from that, and then you direct it to these little circles. These circles are actually planets. And the robot listens to all of that, and then basically comes back and says, do you expect me to accept such a ridiculous notion? So even the robot thought it was crazy. So, but that's interesting because I don't know if you've read this new conversation with this thing called Lambda. which Google has. If you haven't read the full transcript, it's remarkable about how sophisticated the conversation with that chatbot is. But anyway, so the point of this thing is to put some solar panels in space and take the energy and transfer it to Earth. Why? Why do you want to do that? The first question everyone asks. Why don't you put the solar panels up in the desert? You have a lot of areas that have a lot of sun, and then you can get energy. So there are a couple of reasons. First of all, in the space you don't have day and night, you don't have clouds, things of that sort. So you have 24/7 if you put it in the right orbit, almost 24/7 if you put it in the right orbit, of energy. And if you integrate that, it's about 8 times more power than we get on Earth. And then the other one, the ability to send the power where you want and when you want, and as much as you want, to diversify, basically, and just send it to where you want. And this ability of what we call the dispatchable power is very important in actual implementation of the system and why it could be useful. Okay, so how do we go about doing that? Now, there are a couple of basic calculations we have to be aware of. The solar installation at the orbit of Earth is fixed, more or less. It's about 1361, or let's say 1300 kilowatts, 1300 watts per square meter, 1.3 kilowatts per square meter. That's the total amount of solar energy that's available. Now, if you do it at the higher frequencies, and the other thing is that there's this thing, some of you are probably aware of, called the sparse array curse, which means that if you don't place your elements relatively on the order of lambda over 2, or maybe up to lambda, just basically on the lambda over 2 scale, if you have sparsity in your array, what it does, it makes your system energy go to directions you don't want. Some of your energy is wasted. Now, if you're making a communication system, it's okay, because why do you care? As long as the person I'm trying to talk to, if I'm trying to talk to him here, I can always talk to him. I don't care if you hear it too. Fine. But in power, you have to send it exactly to where you want. So that's important. So it means that basically at a certain spacing, your number of antennas increases as you go to higher frequencies. So this is basically an important thing. So it means that the power per element is going to go down that you transmit. But the benefit of doing it locally is that you take the energy and transmit it and eliminate a lot of the DC distribution lines, which are a significant part of the mass. Now, for those of you who have worked in space, you realize that you know that the most important thing, or perhaps one of the most important, I would say the most important thing when you go send things into space is what? Say again? Heat is important, very, very important. I wouldn't say it's the most important thing. Like most things in real life, the real important thing is the economics. And it comes from the mass. How much it weighs. Heat is very important and ties into the mass too. But it's the mass. How much does it weigh? So that's important. So the concept that we've developed in Caltech is basically this concept of what we call a flat system. Systems are flat. Each one of them basically receive the power on one or both sides and transmit the power on one or both sides. And you can actually receive and transmit energy, and you have this number of them flying information in close proximity. And what you do, you have a synchronous operation of these things. And what this does, it allows you to make sail-like structures that can receive power and transmit it locally without having to deal with other things. Now, why is this important? Because of the mass. Now, so this is a little bit of a scaling of the system, so you can think about the different levels of hierarchy. So the unit building block of the system, you can think about it as what we call a tile. A tile is a unit, it basically is about 8 by 8 centimeters, or more or less, maybe something like that, depending on the specific implementation. You can think about strips that are 2 meters by 60 meters, and there are like the units and all. So to give you a sense, tile is something, I've got a broad one, except for the fact that I was pretty sure, I have to kind of like in the airport explain what these things are. It's big, some of them, and then it's got the ring ones, you can see it. So the size of these things, and then the module, which can be anywhere between 20 by 20 or 60 by 2 to 60 by 60. And then the system, that can be between 1 kilometer square to 3 kilometers by square. The latest rendition of our system is about 1 kilometer by kilometer in space. Now, to make something like this, of course, you can't launch something that's 1 kilometer by kilometer. Or even like 60 by 60 or 20 by 20. There's no launch vehicle in the world. And we're working with all of them right now. But there are no launch vehicles in the world that could launch something that's 20 by 20. You have to be able to fold. You have to be able to make it smaller and make it more compact. Now, and we'll show you how that's done. So the question is that can you make flexible molds? Can you make them lightweight and flexible so you can actually roll them and pack them? And if you have something like this, of course, it has a lot of other applications beyond space, because you can deploy them in different ways and can be used for wireless power transfer or communications, sensors, or what have you. So the idea here is that you make these rollable systems, and then you basically pack them into a cylinder that gets unpacked in space. And actually, my colleague Sergio Pellegrino, who's specialty in space structure, is actually working on this at Caltech, and my other colleague Harry Athwater works on the photovoltaic side of things. So we basically grab these things, and we have the structures built. And the idea here is that basically you have, let's see if this video runs. Yeah. So this basically you have this formation flying of these units, and there are different ways to achieve this, which is interesting. So this is a very simple semi-rendition of that thing. And okay, so let's talk about the building. So this is basically a schematic view of our first generation tile, which is basically what we call, it's based on kind of concentrator based, and there's another generation that's coming, which is different. Now, this system basically receives the solar photovoltaic energy and then converts it directly using that IC that I showed you earlier and drives the 16 elements, here the 16 antennas, and transfer power. Now, these are designed so that they can work, it can synchronize with each other across the system. So each one of them has one of those chips and uses it to transfer the energy. Now, these are two big pictures of two generations of that. This is our first generation and second generation. And what you see, this is the total mass of the system, of this tile, with some extras here, about 16 grams. And if you hold it in your hand, you will feel how light actually it is. Now, the size of the RF, all of the RF and power transfer system part of it is less than 8 grams in this system. The rest of it is other things like the photovoltaics and things of that kind, the blinds. And these things are really flexible. You can actually take them, roll them like that. You can take them and bend them and flex them and all sorts of interesting things that you can do with them. So they're very lightweight and flexible. And you can make larger arrays with them. So this is an example of 256 element array that's flexible. This is a different implementation of that. And what you see here, for example, is you can actually bend it. And using this orthogonal basis algorithms, what you see is that when you bend it, initially, so the initially is focusing, and then when you bend it a little bit, you can see that part of it is bent, which you can easily do. Now, it gets all messed up. But the system rapidly kind of adjusts itself using those orthogonal bases and refocuses the power to the right place. And you can see the different power profiles. These are different scans of power. You can see that really the focusing is happening. It's going basically just like going and focusing, and then, of course, it diverges afterwards, and all of those good things that happen. Now, but the question is, if you have something this flexible on a large scale, phased array rely on timing. If the timing is messed up, I mean, yes, you can rely on the algorithm to correct it, but then you have to really know how much has changed. Now, the benefit of the system is that these are mechanical systems. Mechanical systems don't move that fast compared to electronics. Electronics is about the same order of magnitude faster than the speed of light is faster than the speed of sound, which is a million order of magnitude. So electronics is about a million times faster than mechanical systems. So now, the key question is that, can the system detect its own shape? Can you recognize, can the system know what shape it is in when it's bent and flexed, and reconstruct that itself, and use that to make its performance better? Now, so there are different ways to do this, and one of the things that we do here is an example of it. Basically, just the system has, we have RF transmitters and RF receivers on those chips too, which I didn't talk about. So the RF transmitter and the RF receiver talk to each other, and using that information, they can actually kind of do a measurement in situ, locally, of their state, and from that they can reconstruct their own shape. So, oh, by the way, one fun thing that I forgot to mention is that how light these things are going to get, because this is important when we're talking about the flexibility of the system. Right now, the systems we've actually built and tested are at around 500 grams. It's a functional, fully demonstration, and they're not designed to be the lightest. About 500 grams per square meter. It's half a kilogram for the whole square meter of the entire system, all of the features. And now they're basically looking at systems that would be about 30 to 50 grams per meter. And just to give you a sense of how light that is, a sheet of paper, grammage, is about a typical sheet of paper, it's about 80 grams per meter squared. So this is lighter than a sheet of paper. Now, as it changes though, something that light is going to be very floppy, right? And when you have something like that, you need to be able to reconstruct its shape, real time. So these are examples of how this reconstruction algorithm works. So these are examples of the shapes that are reconstructed. So these are examples of this being flexed with different radii of curvature, and these are the reconstructed shapes of the system itself using two different approaches and two different algorithms here. So that's one thing, and then you can see that you can do it for both convex and concave systems. You can actually reconstruct it in various forms and shapes. And this is one done at 10 gigahertz. So that was a 2.4 gigahertz. This is a 10 gigahertz. You can see that you can do exactly the same thing at 10 gigahertz. And you can, this is a picture of basically this is a simple example. This is a small array that's being real-time flexed with this setting. And what it does, you can see in the next, what I'll show you in the next slide, is how this power reconstruction of the receiver is without the correction of the shape. And then shape reconstruction with it. So what you can see is that with time, if you don't do shape reconstruction, you know the power starts dropping rapidly and goes back and up, comes down. But now, because of the shape reconstruction, it's much more flat in this simple example. Now, the next issue to think about is that if you have an array, a large array, how would you deal with timing synchronization? Because essentially, timing synchronization is everything. The basic principles of array. And this is something that you need to really be thinking about, how you do it. Now, the different levels of this. So now when you're talking about the order of sub-meters and all those things, there are these electronic distribution of timing systems that we've done. And basically, then you need to have, again, additional electronic circuitry. I'm not going to get into the details of this, but you have delay lock loops that maintain the timing accurately across the system. And it's an active system, and you have test structures that you can see here, for example, that allow you to see what happens when you have a chain of these things, you have a daisy chain of these things, and how the timing varies and all those things. So these are very important to look at and quantify accurately. Because there's a lot of interesting things that you discover as we were doing this. It's what really gets you in any of these things, the unknown unknowns. The things that you don't know that you don't know. And when you start building things, then you realize how much there are other things that you could have. But the benefit is that we actually did this, and we saw that you can actually, on the scale of meters, you can actually use delay lock loops to accurately control the timing. Now, if you go to orders of tens of meters, what you really look at, and you can look at this paper if you're interested. So now we're looking at optical distribution of the timing information. So we use fiber optics, which is lightweight. And you can actually cross, and we make these chips that actually you can couple the fiber optics directly into. So our chips actually have a photodetector on them. They take the fiber optic input and directly convert it to the timing and generate everything else off of that. So there's no other element involved with it. And it's a fiber optic distributes the timing information and all of those things. And this is an example of a chip that you can see with forward. And the fiber optic is coming from the back side. So the fiber going straight into the chip from the bottom side. There's a hole in there. Now, this is basically to show you how it works. Again, I'm not going to get into a lot of details of this thing, so we use basically 780 nanometer fiber, and then we have 25 meter of fiber here. You can see that the locking happens. And this is really the key test, if you want to know what's happening here, is that you have two of these chips that are connected through each one through 5 meters of optics. So they're optically 10 meters apart. And we put them in different locations, including very close, and we demonstrate that the power addition is coherent by adding more module elements, which basically shows that the timing has been distributed accurately and correctly. So you can see that this growth is right, and you can see the coherence curves and all those things. So that timing is also another aspect of this thing. So now, with all of these things, I want to kind of wrap this talk and just bring you to a thought. Now, about 20 years ago, I was kind of evangelizing and promoting millimeter wave communication systems, and at the time people saying, why do you want millimeter wave? 2.4 gigahertz is plenty high enough frequency, Wi-Fi is great, why do we need anything like that? And I made actually this statement 20 years ago about a different subject, and I'm going to make it about this subject. The bottom line is that the wireless power transfer at a distance is too compelling. So it is not imaginable a future technology where this is not going to have a significant place. That's the bottom line. It will have a place. It will happen one way or another. And it will happen with or without you. Fortunately for the people in this conference, it will be with you. But when I talk to other people, I have to tell them, okay, you don't want to be part of it, no problem. So it will happen with or without you, and I think that's an important one. Now, I'd like to acknowledge a large number of people. Of course, no work really is done by one person, or it's all of the members of the group. And while we're doing that, we also do a video of that tile transferring from the solar simulator, transferring energy wires to a handheld audio. Now, I'd like to acknowledge all of the members in my group and other groups and the Caltech Space Solar Power Project, which has been a very important part of this development. And now there are a lot of new efforts as a result of the work that has been done there. And so this basically shows you what's going on. And with that, I'd like to thank you for your attention and open it to questions. Thank you.
Yeah, thank you, Professor Federici, so much for that incredibly exciting talk. We're open for questions now. We have about 10 minutes.
By the way, while we're getting the microphone, I was hoping that your screen would be fluorescent, because some of these screens are.
Oh, is that right?
Because no, but this one isn't, because I cannot have this UV.
Oh, wow. Okay.
Laser pointer one, so you can indicate fluorescent thing that you see.
So I have two comments and
Go ahead.
questions. First comment, thank you very much for this amazing talk. I think you covered most of what radio colleagues are looking for. Second comment I have is that we have been talking about focused energy, and you bring it in a very clever way. I think Farfield is no longer WPW is really focused there. So these are the three comments. So the two questions I have: first, how do you locate the sensors that you will have some kind of feedback channel that you can go? And the second question I have is, what is the efficiency of your system, assuming that I believe you continue to have secondary loads in the system?
Yeah, so both great questions. Let me talk to them one at a time and then we can follow up with that. So the first question is, how do we find the system? And basically it goes back to that dynamic communication that exists between what we call the receiving units, the RUs and the GUs. And that's where basically there is communication back from the RUs to the GUs, but because of the algorithm that we have, it doesn't have to be one element per time. So it can actually happen in batch. So we go through all of those like funny looking checkerboard kind of like combinations, and the system processes it, and then you get all of the data back, and the system from that calculates what the correct state is, and it naturally finds the system, tracks that we can cover, because it basically finds the phase setting and amplitude settings that maximizes the energy at the location of the RU. So it doesn't really need an XYZ. All it needs to know is basically what are the settings that will maximize the energy transfer. So that's the first one. The second part of your question is an important one, and it requires actually a pretty nuanced answer. So I'll give you the specific numbers and then we'll talk about the answer. So efficiency, right? What is the efficiency? So, okay, the efficiency consists of three main parts, right? Basically. So some people talk about wall-to-wall efficiency, etc. So let's break it. There's an efficiency of conversion from DC to RF. That comes from your electronics. That's the power electronics. You can get something like 60+% with today's designs, with the best designs, and that's something that we know how to do in all those things, and then just basically 60+% efficiency on the transfer. The recovery efficiency, let's talk about that, which is basically how much of the power that's incident on your RU will turn into a DC power. That can be even higher. That's basically 70–75% in practice. And people have reported 95%, but when you look at the report, well, you know how really how to calibrate or not. That's basically what the question. So then 75% I think is a reasonable number there, plus minus. Then what remains is the transfer efficiency. That was what I was talking about in the beginning of the talk, which is basically what fraction of the power ends up in the spot. Now, going back to the side load question, the side load can be overcome significantly by a combination of two things. Making sure that the array is not sparse, the spacing. And the other thing is that controlling the radiative pattern of the antennas. This is the product of how much you get outside is essentially the product of the element pattern times the array, as everyone knows. Right? So that combination, that depends on the orientation, distance, and all those things and the sizes. So that's why I was giving those charts. So that can be pretty high, can be like 89, 90% for anything that's within that limit of range of the radiating near field, the Fresnel range. So the overall efficiency is the product of these three, right? So you can basically come to like 30, 20%, something like that. Now, the key question is, I haven't, so then they can say, okay, well, but if I'm a chemic designer, I'm talking about like 90%, why do I have to worry about 20%? The response, I can give a glib response to this thing, which is basically, what is the efficiency of Wi-Fi versus Ethernet? I've actually calculated the efficiency of Wi-Fi. Just for the heck of it, I did. It's 0.00001%. Maybe 2.002%. I don't know. Exact numbers, but that's order of magnitude. But how many people use Wi-Fi versus how many people use Ethernet? So it's the features, also math. They have to think about it. Yeah. So that's basically. I'm trying to give you a direct, honest answer. I'm not trying to hide the numbers, but that's basically the number. But the question is that is it worth what you're trying to do? I hope I answered your question. Any more questions?
Thank you. I would like to congratulate for this very interesting presentation as well. My first question was exactly the second one of Professor Carvalho, so you answered. But concerning this efficiency, obviously the bottleneck is the transfer efficiency, RF to RF efficiency. How do you have some tools to predict it? Because, for example, if you are in the near field radiative region, the freeze formula doesn't.
No, the freeze doesn't work. Okay. It's that basically that matrix formula that I showed in the beginning. So there was like, maybe I can jump back to that slide. Sorry. I don't think I'm looking at the same slide. Okay, so there was this presentation, there's this, the matrix, you can think about it as basically an N-port, N-port, right? So you have N, let's say you have N-port on the transmit, you have N-port on the receive, right? You have N antennas on the transmit, N-port. You can think about it as a microwave system, you can model it as an M plus N S-parameter matrix. So that matrix covers everything, near field, far field, non-radiated near field, and all. And you can model those things, and then you can basically look at it as that matrix summation, and there was an expression in the bottom of the matrix multiplication that allows you to calculate. So you can actually use that. And when you do that, you can see how close or far you come from the freeze formula.
And this results in 30% efficiency at 24 gigahertz.
Say again?
And this results to you to 30% efficiency.
No, you can get more. Actually, at 24 gigahertz, you can get actually close to 90% of transfer efficiency.
Okay.
Not close to 90% transfer efficiency. But then, of course, that gets multiplied by the efficiency of the conversion to RF and down back to DC. Thank you very much.
Very powerful. Well, I just want to choose, because I can see this is really the multi-physics problem, okay? To talk about, look into this complexity of the structures. Okay? So I can see the thermal problem and the mechanical problem and a bunch of other things. So if we send it to space, for example, for SPS application, how long, lifetime of this entire system under the sunlight, I don't know, do you think it will last more than 10 years? Because most of the space qualifier system for the, if you talk about economic factors, okay, because that's really, if you send it for 5 years, definitely it's not worthwhile. But if you send it for 15 years is really something we expect from most of these system applications. Of course, if you look at the low Earth orbit systems, we'll talk about 5 years. But for this, 15 years should be nominal number, I think.
Right. So that's a good question about the lifetime and its impact on the techno-economic analysis. So the way you think about this, and I will give you the specific answer that to the question you asked, but at least the way we arrive at those answers is not, we're not trying to ballpark it. Yeah, I think 5 is good, 10 is not bad. We've done a full techno-economical analysis, meaning we calculated the estimated cost of the system from the components, manufacturing, and the launch, and we've looked at that, and we've looked at what the cost of the electricity that it generates is, and what we need to be comfortable, and from that we arrive at a number. The numbers we arrive at is actually basically close to what you said, which is basically about 10 years, is where you, 8 years is basically where you break even for that. Now, for systems that we make, our target is basically that 15 years plus, and we've actually subjected them to do all of the things that we can launch in space. We have done all of the space qualification type tests. We do this from vibration testing to radiation testing to vacuum, all of these things, we do all of them. And basically that's the problem. There's also the aging curves associated with the system, as I mentioned, multi-physics system, there's a mechanical part, electrical part. There are also some of these aging and reliability models that you have to take into account. And that's basically where a lot of things that people do in the industry comes into play, how you actually calculate this accuracy and make predictions. People are actually, in the industry, there are people who are very good at calculating these, estimating what the age kind of system is. And we are basically using the same models for models. So short answer to your question is basically 15 plus years. Longer answer is that it needs to be calculated.
Yeah, we expect 50 years. First, that's
yeah, I mean, sure. Yeah.
Of course, we can think about the first generation.
But what happens is the interesting thing is that you change a couple of parameters and that number changes all of a sudden. That number, very easily, that number can become 5. Very easy. And the point of this thing is that if you make them light enough and low cost enough, it doesn't matter at some point. Because you can basically decommission it. If you have some of them that are broken, you just basically let them burn in the atmosphere. On the next launch, you just do more. The so low cost. With each launch, you can basically launch 100 of them.
All right, we are just about out of time. Professor Hajimuri will be with us for coffee break and the banquet tonight, so feel free to interact with that. I love your final slide about how this is going to happen with or without. I guess one of the people going to happen without is Elon Musk, who doesn't really want to work with this. But I hope you were wrong.
No, we will.
We want to provide an appreciation gift. It is wine made by the University of Bordeaux, so it is scientifically validated.
Oh, thank you very much. Thank you.
Yeah.